So you just finished my Fundamentals of Select class that's totally free over on smartpostgres.com. And as part of that, when we were looking at the 8K pages inside ordinary tables, I said down the left-hand side, there's this column called the CTID. That CTID, I said, is a tuple identifier. And during the Fundamentals of Select class, I was like, that's not important now. We're going to come back to it later. Well, the time has come. We need to talk about how Postgres stores multiple versions of rows inside a table. We need to talk about why it does that, how it tries to clean up the mess afterwards. And to do it, I'm going to start by using a minimal stripped down version of the users table so that you can more easily see what's going on. We're going to start by creating that table. I'm going to call it users mini. And I'm going to put a subset of the columns in there, just ID, display name, reputation, and so forth. And I'm going to shove in a filler column just to make the rows a little bit bigger. I'm going to put in 26 rows, one for each letter of the alphabet, Alex, Billy, Charlie, Devin, and so forth. I'm going to insert those 26 rows, and then I'm going to go see what the table looks like on disk. We'll go create it, and then I'm going to go see what my table looks like. I'm going to say, show me all of the rows. Let's get it just right so I can zoom in on it here. So here I'm saying, show me the CTID, Xmin, and Xmax, and all of the columns from users mini ordered by the rows ID. So we have number 1 was Alex, 2 was Billy, 3 was Charlie, and so forth. You see how over on the far left there's that CTID? So CTID has 2 numbers in it. This is a system column that's done by Postgres. I didn't name this column when I created the table. It's automatically added in for me. Postgres added that CTID column, and it stands for 2 numbers. First number is the literal page number. Remember I said in Fundamentals of Select, everything's stored in 8K pages. Page number 0 and then row number 1. That 0, 1 means the first row on the first page. Why didn't they start them both at 0? Why does page number start at 0 and why does row number start at 1? Look, I don't have all the answers. I have a lot of questions about how software was created, just like I'm sure a lot of your legacy software was. But that 0, 1 is the first row or first tuple. We'll start to explain the differences between those. First row, second row, third row, fourth row, and so forth. Now I did say that I was going to put some filler inside there, make the rows nice and large. Because I put some filler in, we can only fit about 10 rows per page. So if I scroll down, you see that 0, 1 through 10, then 1, 1 through 110, and then we've got a handful of rows that are left on the third page. So our object has 3 8K pages. We have page 0, page 1, and page 2. 3 8K pages. And if we want to see how much storage space that's taken up, I can go use that totally free check indexes function that we include in our Smart Postgres bag of tricks. And there's a column in here for size kilobytes. The ordinary table is 24K in size, 3 pages times 8K each, 24 kilobytes. Why is there 2 rows in here? We'll come back to that in a little while. So let's say that we run an update statement because everybody, well, just decided to log in at exactly the same time. If I run this update users mini, there's no where clause on it. So I'm going to update all 26 rows that are inside my table. 3, 2, 1, execute. And now let's take a look at what's inside our table. And something changed. The first row is no longer at 0, 1. In fact, it's at 2, 7. Eagle-eyed viewers will remember that we had 2 full pages, and then on the third page we had 6 rows on it. Well, now user ID number 1, Alex, has been slotted into the 7th position on the second page. Why? Well, what Postgres is doing is it's keeping old versions in place. The original version that we first inserted stays in its place on the original 8K page. And then Postgres adds a new version in a new place. So why does it do that? It does that so as my insert is scribbling away, doing all kinds of work, let's say that I do it inside of a transaction even, as I'm scribbling all this data down, locking it all over the place, well, Postgres now has an old version of the row built into the same 8K pages. So this way writers and readers can coexist. This is called multi-version concurrency control. Now, whenever I do notes for y'all, whenever you're going through one of my sessions, I try to put notes inside here with the same kind of takeaways. I imagine that I was attending the class, and I think about what notes would I take, so then I try to take those same notes for you here. What Postgres is doing is called multi-version, meaning multiple versions of the rows, concurrency control. Concurrency means we've got writers and readers that need to access the system at exactly the same time. If you used other databases like Microsoft SQL Server, you may know that as RCSI, something that's optional that you have to turn on in SQL Server and Azure SQL DB, managed instances, etc. Postgres has it turned on by default, and you can't turn it off, which has some interesting implications. Now, this does mean that Postgres is going to keep old versions of rows inside here, and we're going to have to go back and clean this out at some point. One way we can do it is a command that's called vacuum, vacuuming out all the dead tuples. Now, I should say at some point I was going to tell you the difference between rows and tuples. When you and I select a row out of here, we like to think that there's just one row, but in actuality, there are multiple rows, depending on how many versions Postgres needed to keep inside here. It's going to be 2, old and new, basically. So Postgres may have to keep multiple versions. In order to understand that, they use the term tuple. It's going to be a tuple instead of a row, but you and I can kind of think of it the same way. I like to think of rows as stuff that I'm delivering to users, but when I go behind the database back end, I'm going to have to deal with tuples because there may be multiple versions of it. One way that I can clean out all those dead tuples is to do a vacuum. Now, before I do a vacuum, I want to pay attention to where those rows live. Oh, and I also want to pay attention to how large the table is. Let's go look at the size of our table again with check indexes. Remember, the table used to be 3 8K pages. Now it's 6 8K pages. We needed additional space in order to handle these new versions that we were adding. So we have a couple of problems here. One is that the table has become larger with all these dead extra rows in it. The second is that it's become physically larger, which affects things like backups, for example. So let's go take a look at, sometimes when I say things, I'm like, look, that when I say that it affects backups, if you're doing a logical backup by exporting the rows, you wouldn't be affected. But if you're doing things like a storage snapshot backup or replicating storage, you would be affected. Always want to be completely technically correct, and if I say a gotcha, I want to be careful of that. So we're going to do a vacuum here in a second. We're going to make a brand new copy of the table, but before I do, I want you to note that our rows are now on page, or our tuples are now on page 2, 3, and 4 of the object. Alex is on page number 2, and so forth. Now, let's do a vacuum. So if I do a vacuum, scroll up here and do it, I'm going to do a vacuum full. What this means, and of course it's instantaneous on a table this small, but what this means is that you'd think with a name like vacuum that Postgres is sucking out the dead rows. That's not how it's really working. What it's really working is building a brand new copy of this object. It's reading the old 8K pages, but it's building a brand new set of 8K pages starting from scratch. So once that's done, then I can go take a look and see where my data lives. And now we're back to our starting point where now Alex is on page 0, slot 1, Billy is on page 0, slot 2, and so forth. So this compacted the object, it got rid of the dead tuples, and also the table size is smaller. If I go look in check indexes to see the size of these objects, now we're down to, let's get over here, size are 24 kilobytes. Again, we're back down to 3 8K pages. So at first you're going to think, great, then I probably want to vacuum all the time. But unfortunately, vacuum is a fully blocking exclusive lock operation. It's going to be reading your whole object and then writing out a whole brand new object in its place. And while that's super simple for something that's only got 24 kilobytes in it, it's going to suck pretty bad in your real world objects that have gigabytes or terabytes involved. So Postgres tries to fix that for you by automatically vacuuming behind the scenes. Now, eagle-eyed readers will notice that at the beginning of the demo, I turned off automatic vacuuming. I'm doing that here because I just didn't want, as I go through and I tell you these sweet stories of how Postgres works, I didn't want auto vacuuming coming in behind the scenes and changing things. It would be totally normal for you to think, Brent, you're just setting up Postgres so it can't defend itself. That's not true. I will set up Postgres so that it can defend itself here shortly. But first, I just had to teach you the basics of how this thing works. I just didn't want auto vacuum kicking off in the middle of me trying to explain something. Now, I explained some of the problems, how we have extra space consumed, but for you to really understand how bad the problem is, I need to switch to a much larger table. So in the next module, we're going to switch to the full-size users table, and I'm going to show you the problems that this causes for selects. When your table becomes larger, obviously selects are going to take longer, but what kinds of selects? And how do indexes come into play? You'll learn all that and more in the next couple of modules.